These are the sample problems I did in class on Wednesday. You should be able to use these to help you understand how to solve the problems that are due for our virtual assignment today. You may have already done those in class, maybe not done those in class, but I want to make sure I gave you these examples. So I'll upload this as a PDF, and I'll also have this screencast. So basically, Newton's second law says that acceleration is directly related with the net force, so meaning more net force, more acceleration. Acceleration is inversely related with mass. So more mass for the same force would give you a lower acceleration. So this is the formula for that. It should be now as formula 5 on your new yellow formula sheet. And to the right, you would just say that's the formula for Newton's second law. You could rearrange this formula to look like these versions in purple. And remember, you can always use this triangle to help you figure out. So force on top, mass and acceleration on bottom. So force over mass is acceleration, force over acceleration is mass, and force is equal to mass times acceleration. So these are all three versions of that formula. The first sample I did said assume a person weighs 490 newtons on Earth. What's the person's mass? So you need to know that weight is a gravitational force. So I'm using this version of the formula. I've got the 490 newtons of weight or gravitational force. And on your formula sheet, and as we've discussed before, the gravitational acceleration on Earth is about 9.8 meters per second per second. If you use 10 meters per second because you like to round, you get a slightly different answer here, 49 kilograms instead of 50 kilograms. But notice I'm using the three-step method. So general formula first, plug in numbers with units, final answer circled with units. The last part of this, and I had to squish it here because I forgot about that, is if that person accelerated at 3 meters per second in a car, what's the force of the car on the person? So the car would have to push the person forward to accelerate the person along with the car. So we'd use this version of the formula. Plug in numbers, 50 kilograms times 3 meters per second, and this is 150 newtons of force. Sample 2. Assume we have a lunar lander, so lunar means moon, that has a weight or gravitational force of 10,000 newtons on Earth. Find the mass of the lunar lander on Earth. Well, going to this version of the formula, the force was given as 10,000 newtons. I'm still using 9.8 meters per second, but again, you could use 10. So I get 1,020 kilograms of mass. The mass of the lunar lander on the moon would be the same. So a lot of people in class had trouble with this. They try to do the math. But you need to remember that mass is based on your total amount of stuff that makes you up. That's atoms, so the protons, neutrons, electrons, all that stuff we talked about first semester. And that's going to end up being the same pretty much anywhere in the universe. At least for this level of course, we'll say that. For C, what's the gravitational force of the moon on the lunar lander if the moon's gravitational acceleration is 1.6 meters per second? So we'll go back to this version of the formula. We know the mass, 1,020 kilograms, and the moon's gravitational acceleration is 1.6 meters per second, so that's around 632 newtons. General formula, plug in numbers with units, circle answer with units. The last one, sample 3, assume a shopping cart with a mass of 20 kilograms is being pushed with 50 newtons of force and also experiences 10 newtons of friction. I did not say which direction the force was acting. So in this particular case, it doesn't particularly matter. I'm going to move that off and get my scribble out of there. It doesn't particularly matter which direction the force is acting. I know it would be going sideways. So gravitational force is down, normal force is up. When you do make free body diagrams, you need to label the forces. The downward and upward forces should be the same because the shopping cart isn't accelerating up to the heavens or down to the center of the Earth. The applied force I had going to the right, the friction force I had going to the left, in opposite direction because friction does oppose motion. It tends to cause things to slow down. So this is a bigger error than this because those forces are unbalanced. For the last part of this question, if I'm wanting to determine the acceleration of the shopping cart, I used this formula, which was on the front of the page. It's Newton's second law. But what I need to recognize now is the net force is only dependent on these horizontal arrows. Since the vertical arrows cancel out, I don't need to think of them because the forces vertically are balanced. The horizontal forces are not balanced, so since the applied force is bigger than the friction force and they're pointing different directions, I would have 50 minus 10 newtons divided by the mass. That's a net force of 40 newtons, an acceleration of 2 meters per second per second. If for some reason I had multiple forces going in the same direction, then instead of subtracting the 10 newtons from the 50 newtons, I would add all the forces acting in the same direction and just subtract forces acting in the opposite direction. And that would be how we get our net force. Remember, the net force is the total unbalanced force of the system. So I think this is a really nice one relating the free body diagram to Newton's second law. Hope that helps, and that it helps you understand how to solve those problems. Make sure you get that worksheet turned in by 3 p.m. today on March 18th. And you can submit it either as a upload it as pictures from one you did in class yesterday, or complete the document that's online.